Mastering chemistry together.
Can we also do number 28?
Because it says F of HE equals,
And then a percentage.
it's just like it's almost like an italicized F.
Is that flow rate? Is that a flow rate
I'm
also?
guessing that's what flow rate means. But and then the answer has a percent with it.
Or okay.
27.
Oh, I'm still off here. Okay, there we go. All right, so this is on the chapter 5 homework. We can do a couple, but then we really got to get into the next part here.
I was able to figure everything else out except for 27 and 28.
All right, so 1, 2, 3, 4. It's like 109 or something, right? This one. Okay, has anybody else given this a try yet? You got this reaction. Ammonia is injected into the exhaust stream of a coal-burning power plant to reduce the NO to the N2. And here's the reaction. The ammonia reacts with the NO and oxygen to make N2 and water. The exhaust stream of a power plant has a flow rate of 335 liters per second at a particular temperature. And there's 21.4 torr of NO in that exhaust stream. So what should be the flow rate of ammonia delivered at that thing to react completely with the NO if the ammonia is 65.2% pure? All right, so a few things going on here. One thing that seems a little tricky is that the answer is asking for a flow rate in liters per second, which sounds different from what we've normally done. But in this case, that can be treated kind of the same as volume, because you're going to use this volume to do the initial calculations. So you can just kind of assume assume it's 1 second. How much of this is there, and therefore how much of this do you need in that 1 second? And then that's going to scale to any other thing. So when you find the volume of NH3, then you can just put that, like, that's your answer. Just because it's a flow rate doesn't change anything. Now the other part of this is that the reaction is the ammonia is only 65.2% pure. So that means you need more than what you calculate based on the stoichiometry to account for that fact. So you need to do a conversion factor of 100 over 65 to account for that extra that you need to put in so that you get the actual amount of ammonia that you need. So let's take a look at some of that. I don't think we need to solve this whole thing out, but hopefully I can help you organize it a little bit. Actually, I'll leave that there and I'll do it on the board so we can see it.
So I understand how to do all of it and plug it in, but in your quote unquote like conversion factor little series with the x, the fractions, are you just adding a random one that is 100 over 65.2? Or are you doing that after the fact?
Either. Should be fine. So the way you're going to get started with this is to do the stoichiometry to figure out how many moles of ammonia we need per second for 335 liters to react 335 liters per second with the NO2. So if you've got let's see what, of course I've covered up that part, but you've got 21.4. Marker's dead. 21.4 torr of NO. Okay, so then we can convert that to atmospheres. Okay, and And then we know that we can calculate that our moles of NO, and so this is going to be moles per second, basically. Like everything that we're calculating here ends up being per second because it's liters per second. So we still can do the same equations, we just keep in mind that it's really moles per second. And if we keep that per second in there, then everything should be okay. So our pressure is 0.0282 atm. Our volume is 335 liters per second. And then we've got our R and T, which is 955. Okay. So you see here what happens is because our units are all mostly the same, atmospheres cancels, liters cancels, kelvins cancel, and so we end up with moles per second as the product, whatever that is.
How do kelvins cancel with the moles at the bottom?
Because this is moles, the constants in moles per Kelvin, so it's like on the bottom of the bottom, so it's really on the top. Yeah. So what did that come out to? 0.120. So that's going to be moles of NO per second. And then we can do the stoichiometry to figure out moles of ammonia per second. It's 1-to-1 in here. See that? Because it's 4 and 4. So that means we also will need 0.120 moles of ammonia per second. So then, really, so the answer would be the same, right? Because we'd plug that back in there. Well, no, I guess not, because we're gonna, because we've got different pressure and stuff over here. So we can't. So normally we would take this and we go, okay. So the flow rate would just be this plugged into the gas equation with those things, with 765 torr and 298 K. We solve for volume, and that's the answer. But we don't need 0.120 moles of ammonia per second. How much ammonia do we need per second? Do we need more or less than that?
More.
We need more, because our stream is only 65.2% pure. So we have to multiply that by 100 over 65.2, because it's only 65.2% pure, so we need an extra X amount to account for that. Right. So we actually need 0.184 moles per second. Moles of NH3 per second. And then we can do the rest just regular gas law stuff. Yeah? Okay. So that's kind of the tricky part of this question. Also, don't get thrown off by this per second business,
So then
because it's a flow rate instead of a...
That number, can you plug it back into the original, with the PV, was that our
Right, because you're given a new P and T for the ammonia, 765 torr and 298 K.
And this is N, and then you're solving for
Right.
V.
And then you're solving for V. Yep. Okay. And you said the next one too? Let me look at that one. Okay, so the reason that this is given in an F, I don't know if you see that, it's a little weird. The answer says F. I assume that's just because it's like a percentage, like the percent that it's decreased. All right. So what's going on here is effusion again. So the air, a balloon is not a perfectly airtight system. There are small pores in the balloon. There's small leakage by where you tie the balloon, and so over time, whatever's inside the balloon will come out of the balloon. So this is telling you that you have air, and you have, in one balloon, you have helium in the other balloon. The volume of the air-filled balloon has decreased by 5.2%. So what does that mean about the helium balloon then? Do you expect the helium balloon to have decreased by more or by less? First, before we start getting into how to actually calculate this. If you have one balloon filled with air and one balloon filled with helium, and air is nitrogen and oxygen, we're just going to assume that air is just nitrogen and oxygen. Would you expect the helium to effuse faster from the balloon or slower? Faster. So we would expect that percentage to be lower and to be proportional to the effusion rate between those two. Or the difference in the effusion rate between those two. So we can basically set up a proportion here. Air is 4/5 nitrogen and 1/5 oxygen, which means we can take from its effusion rate that it's going to be basically a weighted average of those molar masses. So let's grab our equation here. All right, so the ratio of the effusion rate between the, let's say, the air and the helium equals the square root of the inverse of the molar mass ratios. Okay. So the tricky part here is there is no molar mass for air. So we're going to use a weighted average of what it tells us to assume air is. So the molar mass of air is going to be, what did it say? 4/5 nitrogen and 1/5 oxygen. So that's 0.8 times N2 molar mass, which would be 28, plus 1/5 or 0.2 times the oxygen, which is 32. All right, and so we call that the molar mass of air, is the weighted average of those two molar masses. Okay, so then we put that here. We've got helium here. We call this rate 5.2, and then we solve for the rate of the air that way. Let's see if that's right, actually, because I wasn't. Yeah, so if you stick with that, that should work, because this that makes sense. Okay. So if you can't get it to work, it's 14 is the answer.
If you need 5.2.
Yeah, but we have different.
Did you get different numbers? Okay, so whatever you get, that should be how you work it.
So what did you do after you found?
Yeah, what is going to be on the rate of air and the rate of helium?
And what do you do with the percentage that it increases?
You don't need to do anything with it. So you can make the ratio of the two percentages is the ratio of the effusion rates, because if one is effusing twice as fast, it will lose twice as much volume.
So you don't need any numbers on the left side of the...
Well, this one's going to be whatever you're given, so 5.2, or no, this one is going to be 5.2 because the air balloon has
and you're
decreased by
solving for
5.2%,
helium. Okay.
and then you're solving for the helium one.
And then you have to do times 2 at the end? Or no?
No,
You're
no.
just knowing in your head that it's going to be, you said twice as fast because it's smaller.
Oh no, I just made up a number.
Okay.
Yeah. So it's not twice, it's almost 3 times as fast actually,
Okay.
because for 5.2. So you should get a number that's a little less than 3 times whatever you're given there. Okay. Actually, let's start a new file here. All right. So we do something a little bit weird in this part of the semester. Most general chemistry books go into, well, I guess it depends on the books, but a lot of them go into this thermal chemistry in chapter 6, where we calculate the heats of different reactions and all of this stuff. At Harper here, we save that until the next semester, because normally the way that it works is we do this chapter 6, and then you have to do way more of it in the second semester anyway, so it always seemed like not that useful to kind of do it now, and nobody gets it, and then do it again later. So instead of that, we're just going to look at a couple basic concepts, define some terms that we're going to need later from chapter 6, and then basically skip the rest of the chapter. So we're not going to do any homework. There's not really going to be like problems from chapter 6 to solve, and we're going to get into more of the interesting stuff in the descriptive chemistry in the next stuff. So let's do that, defining some terms around heat, energy, work, these kinds of, work doesn't have any in it, those kinds of terms. We've talked about these a little bit, but let's apply them to chemical reactions. All right, so we know about conservation of energy. What is conservation of energy? Or I guess we talked about conservation of mass. We didn't really talk about conservation of energy. I'll give you a hint. It's the same. So what is it? What do you think it says?
Energy can be created or destroyed, can only be transported.
Yeah, energy isn't created or destroyed, it's only transferred. So you can move energy around, you can't get rid of it. So we have conservation of energy. Destroyed. All right, there are 2 ways you can transfer energy. Heat and work. Heat is the flow of energy caused by a temperature difference. So if you have a higher temperature in one area, a lower temperature in another area, energy will flow from the higher area to the lower area, and that's called heat. If you have a force applied to over a distance, that is called work. So like in the physics realm, we talk about like, okay, you push a mass a particular distance, so there's a force that's gone over that distance, and that's the work that you've done. In chemistry, we often define work as pressure times a change in volume. Because in chemical work, usually what that means is you have an open system, so you do some reaction, and it like emits a gas or something. Like you think of an explosion is increasing the volume at an external pressure. So something, if you do a reaction and it makes a gas, that gas has to come out, and that coming out is doing work because it's pushing on the atmosphere in order to come out. If you have a closed system where nothing can come out, no like gas can come out, and nothing changes volume, if it's a constant volume system, then you're only heating. then you're only transferring energy via heat. In chemistry, we often talk about heat. Now, heat has its own definition, but we talk about a particular type of heat called enthalpy. And yeah, I don't want to skip all that stuff. Actually, no, that's not quite right. Let's not say that. That's not quite right. Heat is often given as we'll keep this separate because I don't want to confuse you guys. Heat is given as Q. It is usually shown as Q in these equations, and enthalpy is a little bit different. Enthalpy is like a change of heat in a system, right? But it depends more on it depends on a change in energy and the change in work together. So because heat is not, or energy is not created or destroyed, if you do a chemical reaction, let's say it releases heat. So what's happening? Where does that energy go? Yeah, in the air, or to the surroundings. So another important definition here for chemistry is that we usually define two kind of domains: the system and the surroundings. And actually, while we're being correct here, let me go also and correct this. There is also a force over a distance. It's just that in chemistry, we're often most concerned with pressure volume work. All right, so we have system and surroundings. Now, this is a totally arbitrary distinction. Whenever there's some sort of process where energy is transferred, you can define what is the system and what is the surroundings. And if energy goes from the system to the surroundings, it's always negative. So depending on how you define that can have some different meanings. So for instance, when you sweat, that cools you down, right? Sweating, everyone knows how that works. Your sweat glands push water out to the surface of your skin. That water evaporates. Evaporation is an endothermic process. It requires heat going in, and so that cools you. So let's say that your skin is the system. Which direction is the energy moving? Is it going from the system, you, to the surroundings, or is it going from the surroundings to the system? If you are the system and you are sweating, where is the energy going? Yeah.
Doesn't the energy go into the sweat and then evaporate out?
Right. So if you, your skin is the system, then we would say that the energy is going to the surroundings. So that's an exothermic process that would have a negative change in energy. But what if the sweat is the system? What if we're looking at the sweat itself, the water? Where is the energy going then? Yeah, then it's into the system. So depending on how you define the system and the surroundings, you could have a totally opposite answer. Right? The good news is that for chemistry, we usually define these the same way. The system is the atoms, elements, and compounds. That are actually participating in the reaction. Yeah. Question?
Can I just rephrase what you said in a different way? I don't know. I just
Sure.
want to make sure I'm understanding it right.
Yes.
So heat goes out as exothermic and heat comes in as endothermic?
Mm-hmm. Yep. But that out and in may be different depending on how you define what's out and what's in, right? So usually in chemistry we talk about the system as the atoms, elements, and compounds, and the surroundings as the things like solvents, glassware, the air, whatever, stuff that's not those. All right, and here's where it can sometimes get a little bit tricky. So let's say you have an endothermic reaction. How does an endothermic reaction feel when you touch it? If it is taking energy in, how does it feel?
Or no, it's cold.
Yeah, so that's the tricky thing, right? It's the atoms, elements, and compounds, the molecules are taking the energy in. They are taking the energy from the surroundings, which includes the solvent and the glassware and your hand and whatever. So if it's taking energy from all of that stuff, that means it's actually going to be feeling cold. Even though it's actually increasing in energy by being
It's
endothermic.
taking on the heat. So.
It's taking the energy from the surroundings, and that makes it feel cold.
And heat always goes towards the lesser temperature. That's why
Right.
I believe it's like heat rises. And, well, that's based on the weight of the air and based on temperature. That's a different thing. Never mind.
Yeah,
But
that actually works.
If you open your window on a summer day, you're actually going to have the heat on the inside. That's why when your parents say you're going to chill the world, if you leave the window open, they're wrong. You're just going to heat the indoors.
Right. Yes. Yeah. Because we have to. Yeah. Right. But speaking of that, since we were just talking about that in the last chapter, why does hot air rise? Anybody know?
Because it's.
So you heat up some water, or you got some air, right? You got like a balloon filled with air. You heat up the air. It goes up, like a hot air balloon. Why? Yeah, because it's less dense. So there's less, right, less gravity. Yeah. Assuming constant volume.
That's why fog machines work.
Is that what?
That's why fog machines work.
Is it?
Yeah, it's cold.
Because it's more dense. That's why you can actually see the vapors. So it stays more on the ground.
Oh yeah, because it's more dense than air. Because it's usually propylene glycol, I think, right?
Yeah.
That's the same stuff they make the like vape juice out of. All right, so that's heat and energy and work. I think we'll be okay with that. But these ideas of like exothermic and endothermic and system and surroundings and which direction the energy is going, that's something that'll come back in a little bit. Okay. All right, let's talk about the weird stuff. What?
It's all been normal.
It's all been normal up to this point.
Okay.
Now is the weird stuff. All right. The quantum mechanical model. It will be eventually. We have to get there first. We probably won't get to orbitals until Monday. Yeah, we got like 100 years to cover here. No, not quite. It's like 50 maybe.
Is this the same thing as quantum numbers?
No, but we'll get there.
Okay, sorry.
It's okay. I'm glad you're excited.
I'm not.
Okay.
I mean,
All right, so we need to know some things about light, and then we're going to talk about how light is weird, and then we're going to talk about how electrons are even way weirder. Okay. So electromagnetic radiation. Also known as what's another name for electromagnetic radiation?
it was the first letter.
L. Light. Light. All right. So this is energy, right? It's a type of energy. It's pure energy. It's basically oscillating electric and magnetic fields. So it's wave-like. It's oscillating. It's going back and forth. And there's lots of different types of light that we can measure based on a couple characteristics of it. So when you hear the word radiation, we usually think of bad things. We usually think of nuclear radiation, that sort of thing. But the truth is that radiation simply means the emission of something from a source. So in most cases, we're talking about any kind of light. So these lights are emitting radiation in the form of visible light. All right, so there are various types of light across what we call an electromagnetic spectrum. I don't know where'd my pictures go. Hold on, I gotta start the pictures up again. So let's take a look at the electromagnetic spectrum.
That's Schrodinger's cat.
Yeah, there's Cat. We'll put this one in the notes because this is important. All right. So if light is an oscillating field, that means that we can use the characteristics of a wave to describe it. And that's exactly what we do. So this is the complete electromagnetic spectrum, going all the way from the very low energy, which we call radio waves, up through microwaves, infrared light, visible light, ultraviolet light, X-rays, gamma rays. So whether we call them waves, like radio waves, or microwaves, or whether we call them rays, like X-rays and gamma rays, or whether we call them light, like infrared, visible, ultraviolet, those are all interchangeable. This all comes from way back when it was not necessarily clear that this was all part of the same thing. These rays were kind of detected and nobody really knew what they were. There's also like cathode rays, which is actually electrons, but they thought it was like a beam of light. So a lot of this language comes from those times. But it's all light. It's all light. And the light that we can see is this narrow band that's expanded for you right here. And you'll notice that this is on a wavelength scale. A wavelength scale. So if we look at a wave, okay, let's say there's our wave. So we define one wavelength as a complete oscillation from one point to the return to that point. So like in this case, with this wave, we might say that this is one wavelength. All right, the Greek letter lambda is used to represent wavelength. And so the larger the wavelength is, the more spread out those wave crests are. So what would you say is the relationship between the energy of a wave, if you're looking at this here, between the energy of the wave and the wavelength? The shorter the wavelength, the higher the energy. Because we see the high energy side is way over here, and that's with the really, really short wavelength. So that's waves that are going like this, right? And then the opposite is true on the other side. The low energy waves, the radio waves, are very long wavelengths. So that's in meters. So radio waves from crest to crest could be a kilometer or more. Now notice that when we talk about energy and these things, we're not talking about intensity. So you can still have very low intensity or very high intensity light at any of these points on the spectrum. The intensity is more proportional to the height or the amplitude of the wave. All right. Okay, so another way that we can look at this is something called frequency. So we define this idea of wavelength. What's frequency?
How often it occurs.
So it's something about how often something happens, how often what happens. Yeah, it's how often you're completing a wavelength. Now, how do we time that? What does that mean? Like if we're looking at that wave that we just drew, what do we mean by time? That's not a time-based drawing.
Maybe if it's that same distance, but there's 86 wavelengths in that distance.
So that's true, assuming then that the x-axis is a time scale, right? So if we imagine that x-axis is a time scale, and we imagine the wave is propagating through time, then the frequency is, we could say, how often does it complete a period? And that's exactly what what it's measured here. Now, this picture from the book is actually wrong. Does anybody see a mistake? I just noticed it. Probably not, because we're just talking about this for the first time. But the symbol for frequency is the same as wavelength, because that is wrong. Yeah, frequency is the Greek letter nu, which kind of looks like a V, but it's not a V. And yeah, I just noticed that's wrong in the book as well. So I mean, good thing they got a new edition for hundreds of dollars and fixed all their mistakes, right? Anyway, so that's frequency. So that is in hertz. Now hertz, H-E-R-T-S, or T-Z, sorry, is another way of expressing that unit is inverse seconds, or cycles per second, or seconds to the -1. So this is how many periods of the wave are completed per second. And that's that top number. So you'll notice that those are all pretty big numbers. Even on the low energy side, you're talking about thousands of cycles per second. So the light's moving fairly fast. Now, does that mean that the higher the frequency, the faster the light goes? No, because light always moves at the speed of light. It's constant, right? So it's how many periods are, or how many cycles per second. Okay. So a couple things about the spectrum. As we said, intensity of radiation is not related to the energy of radiation. That's going to become important in a little bit when we talk about the photoelectric effect. But also, we do have a point here where we talk about ionizing radiation. What do you think that means? What do you think it means for radiation to be? Have you heard that term, ionizing radiation? Concentrated radiation? Quite. What does it mean to ionize something? Yeah, you make ions, right? You get rid of electrons. So, what?
No, it's the most dangerous one for us because it's basically changing the matter decomposition of the body.
Yeah. So the reason that we draw a line at this idea of ionizing radiation is because if radiation is strong enough to knock electrons off of things, then that can really mess with you, right? That can really mess with your body. So when we talk about like ultraviolet light causing cancer, did you know that it does that? Yeah. Put on your sunscreen, or put on your sunscreen today.
It causes thymine dimers. So it causes the thymines in your DNA to, instead of bonding across strands to hydrogen bond with each other.
And so there's a lot of different processes that different types of light can do to your DNA, and when your DNA gets messed with like that, then it's not replicating properly, and that's what we call cancer in many cases. So there's a lot of different causes of that, of course, but there are other types of ways that ionizing radiation can damage you as well. Like you can just get burns, like you can get X-ray burns. If you're exposed to too many X-rays, you can have other types of issues, like if you have a lot of X-ray exposure, like medically, like you need a head CT scan or something, they're going to keep track of how often you get that done, because you're only supposed to get a certain number of those per year, or you can start having some negative effects from that.
Okay, but like they always have you like wear a vest or something, like is there something in the vest that makes you not get these?
Yes, the vest is very dense and is usually made of something like lead, or they may use other things now, so that the X-rays can't actually penetrate through that as well.
Can we have visual representation of this by the whole snapping? I need a
By
visual
what?
representation. Is the new Avengers?
Oh.
No,
Dan,
sorry.
there is something about that.
I'm behind on that. I haven't
There's
seen
a whole
a
video of that.
single Avengers movie.
Has no one seen the new Avengers?
I have.
Did the Hulk snap and then it destroys his arm?
Yeah, there's a video about.
And what does that have to do with
This
this?
is the Hulk. They explained it as it's all gamma radiation. So,
When he snaps, he emits gamma
so
radiation.
The Infinity Gauntlet emits gamma radiation.
Does it give a frequency or a wavelength?
It does not.
Oh.
But it's a good visual representation of
There's-
how those can destroy.
All right. Well, thank you.
Yeah, like the entire world.
Good visual.
Okay, I'll see it. It seems like such a project at this point. Like there's so many movies, and it's like hours and hours, and I don't even want to get started.
But there is a video explaining everything about with the snap and the gamma radiation. Actually, what happens is final person to snap the gauntlet.
Pretty cool.
And what happens to his body.
So a few other tidbits about this. Not that we're getting off track or anything, but some other things to note is it's good to have a sense of at least general numbers on these because they're going to come up a lot in the next week or so as we talk about these things. But to know like the basic range of visible light, because when you're solving problems about these things, as we will in a little bit, if you get some crazy number that doesn't make any sense, you're not going to know that it doesn't make any sense if you have no frame of reference. So knowing that the visible light is between about 400 and 750 nanometers. Also, it's going to be really helpful to know how big is a nanometer. Can we convert from meters to nanometers? Yeah, to the 9th. Great. So there are, so 1 meter is 10 to the 9th nanometers. 10 to the minus 9 meters is 1 nanometer. Right. So that'll be helpful. Some other things you notice on the spectrum that sometimes surprise people, microwaves are lower energy than light, than infrared light, just above radio waves. They are not ionizing radiation. I don't know if people still get this, but like it seems like people in my parents' generation are really like afraid of microwaves and believe that like if you microwave your food, you're giving yourself radiation poisoning and cancer and whatever. Has anybody heard that from anyone?
Yeah.
Not real. Yeah.
But if you do eat too many bananas, you could get cancer.
Well, if you eat too many of anything, you can. I mean, cancer is just like a natural process. It's just a thing that happens from like getting old.
Too many
And there's potassium.
So getting back to the Avengers.
Yeah.
Yeah, so you can talk to your parents and other people about that. It is true that being exposed to microwaves can do to you the same thing that it does to food. If they're at high enough intensity, they can kind of heat you up from the inside through the resistive heating process. But it's not true that they do some sort of damage that's related to their ionizing capability or that it's something cancer causing. All right. So we'll get into interference and diffraction and stuff in a little bit. But let's look at some weird stuff that happened. Does anybody know why? Anybody heard of Albert Einstein, the scientist? Sounds familiar? Does anybody know what he won a Nobel Prize for? So everybody says theory of relativity, but it's actually not. It's something called the photoelectric effect. Yeah, describing it. So here's what happens. And this maybe doesn't seem weird at first, but I'll try to make it sound weird by explaining it badly. Okay, so you've got this thing called a vacuum tube. Vacuum tubes we don't use so much anymore, but they used to be a major important component of electronics because they were a way to amplify signals and to make switching devices before we had transistors, which was what most electronics are made out of now. So if you take an evacuated tube and you put a couple electrodes in it, this is a special type of a vacuum tube that would just have these two electrodes, and you have a metal surface of any particular metal. You pick one, whatever. What was found, or what was first known, was that if you shine light at this piece of metal, you can emit electrons from the metal, and those emitted electrons will transfer through the vacuum, because the vacuum inside there, so they don't hit anything. They go directly to the other terminal, that creates a current, and you can measure that current. So you can say, as the light hits this thing, it causes the current to flow. And what was found is different types of metals had different types of light that would make their electrons become emitted. So that's fine. So the weird part that was happening is that there seemed to be this threshold frequency. And this is this idea of intensity versus energy. So let's say that this is some type of ultraviolet light. So if you use any kind of light with an energy below that, visible light, let's say, you put the strongest visible light source you want on that metal, and it will not liberate the electrons. But as soon as you cross that threshold frequency and you have light that has just enough energy, suddenly it does actually respond the way you would expect, that more of that light releases more electrons.
Can you go back to the slide before?
Yeah.
So when you're talking about light and then it emits the electrons, so the actual number of electrons doesn't matter because it has to reach a specific threshold in order to activate those specific electrons.
Right, but then once it does increase that threshold based on the frequency of light, then it has that expected behavior that the more light you put in, the more electrons are coming out, the greater the current.
The amount of electrons does not make a difference in like the light itself, because what depends on it is a certain threshold that it needs to meet before activating those specific electrons.
I think that's what I'm saying, but
Now I'm just more confused.
now you're just more confused.
Yeah,
All right, so let's go back. Let's go back to what we were looking at before. All right, we'll get this worked out. So going back to the spectrum, so we can talk about, and it maybe makes more sense actually when we go a little bit further. We talk about the frequency of the light defining the lower or higher energy of light. So what that photoelectric thing is saying is, if we have, let's say we have light that's here on the spectrum, okay? You pump as much of that light as you want into that metal, no electrons come out. Okay, but now we're over here on the spectrum, we've crossed that threshold, and even just a small amount of light will cause some electrons to come out. And then more light will cause more electrons to come out. This didn't really make sense initially because it seemed like the more light you pump in, eventually you're still getting enough energy to get something out. So why wasn't it coming out? And so what Einstein proposed was that light is actually little, it's not like just this thing that keeps adding up. It's little packets. And those little, anybody know what those little packets are called? Yeah, photons. So he said, what if we assume that light is in these little packets called photons? Then we can make sense of what's happening in this photoelectric effect, because as long as that little packet has enough energy, it doesn't matter how many packets you throw at it. So what he was saying was, if we're back in that lower end of the spectrum, each of those packets is going to have a particular energy. And it doesn't matter how many packets you throw at it, if each one doesn't have enough energy, you're not going to be able to liberate those electrons. But at the higher end of the spectrum, each packet is going to have more energy. So throwing those packets at it, even just one little packet, is going to be enough to throw an electron off of that metal. And so that theory worked. And, that was kind of an interesting thing, but it ends up having huge, huge consequences. So what Einstein proposed was that the energy of that photon, of each of those photons, depends on the wavelength or the frequency. So this is our frequency, nu. And this is a constant called Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. Like most constants, it has kind of a weird unit. You don't have to memorize that, just like your other constants, but by the time you finish the Chapter 7 homework, you probably will have it, just from using it a whole bunch. So remember also that the frequency and wavelength of light are related in that their product is the speed of light. So wavelength is in meters, frequency is in inverse seconds. Multiply those, you get meters per second, and that's the speed of light. Right, which is 3 point. Binding those equations, then, we can also determine the energy of an individual photon by its wavelength.
Well, so the 6.626
JS, joules seconds.
Joules per second, okay.
Not joules per second, joules times second. Joules per second will be joules times 10 to the negative 1. All right. So so light can be considered as these little packets, these little photons, where each photon has a particular energy that can be calculated by the wavelength or the frequency of the light. That's sort of where we've gotten to so far.
Is that like with solar panels, like why you can't shine a flashlight at a solar panel and it like would create energy in the sun?
Kind of. So there's a lot of different kinds of processes going on inside of the solar panels depending on what they're made out of. You can think the idea of this threshold frequency is similar, but it's not the same process. You're not actually like releasing electrons in the same way. You're promoting electrons from something. I don't know. I'm trying to decide how I want to explain it without like getting into it. But electrons are in the valence band. They get promoted to something called a conduction band, and that causes the current to form. They're not like liberated into a vacuum in the same way. You can actually you can get light sensitive things that are tuned to a variety of frequencies of light. The issue is like finding the best efficiency for the light that gets to Earth from the sun. Yeah. All right. Okay, so we figure out now that light is in these little packets. Great. So the next thing that happens is we look at something called atomic spectroscopy, which was kind of a mystery for a while, kind of like the photoelectric effect. So these are some tubes, and we'll look at them in lab on, actually probably not till next week. They might be up there this week, we'll see. But what you do is you fill an evacuated tube with a pure element, pure gas of a pure element, and you pass a current through that, and it emits some pretty light like that, and we'll see some of them. Like neon lights, that kind of thing. That's how that works. That's fine. But when you look through that with a prism, so you actually separate the waves, separate the types of light into the spectrum. Have you ever looked through a prism? Okay, so we're going to do some work with that in lab next week. But this is what you find that's a little bit weird, or was a little bit weird. The individual elements, when you look at their spectrum, have spectral lines. So rather than just a bunch light coming off throughout the spectrum, they have specific lines that they give up. And the reason this is weird is because other types of things that give off light, like if you heat something really, really hot, and it gives off light, you know how something will get like red, and then it'll get yellow, and then it'll get white? That's emitting basically this kind of a spectrum. It's emitting everything all throughout the spectrum because there's all kinds of light coming off.
So kind of a fire or something for that one, right?
Sure, although as we'll see, that's kind of influenced by this as well. But yes, so if you're like heating something up really hot, like a solid, then you kind of emit all kinds of different light, like a light bulb filament. But if you take pure elements in their gases, or not even pure elements, compounds as well, and you excite them, they only emit light at these very specific places. So like helium here only emits light at these various places on the spectrum. And barium only emits light at these various places on the spectrum. And that didn't really make sense to people for a long time. Any idea how we solve that one? So what could be happening inside of an electron or inside of a atom that makes it only emit light at specific spots rather than just whatever kind of light it can? I think what? Kind of. So that's how you emit infrared light, but this is visible light because we can see it. But the idea, it may be, it does, yeah. It has to do with the electrons, and the idea that if the electrons can only have certain energies, discrete energies, then they can only emit certain energies of light. And that's where this word quantum comes from. that it's, well, the quantum was the kind of the name for this little packet, but also this idea that there are discrete quantized levels that energy, that electrons in atoms and molecules can be at. And they can't just have whatever energy they want. And let me show you why that works. So the thing that was developed, if we look at a hydrogen atom, now a hydrogen atom just has one electron. And if you assume that that one electron can be at specific levels, then you would expect it to emit energy when it transfers between those levels from a higher level to a lower level. But there's only a certain number of ways that it can do that. So like in this picture, it can go from the 5th level to the 1st level. It can go from the 4th level to the 2nd level. It can go from the 3rd level to the 1st level. But there's only like so many different ways that it can do that. It can't hang out in between the levels. And that explains the lines, because that means that like you're always going to get energy coming out at 434 nanometers when the going to be possible. And so that explains this idea of atomic spectra, because now we say that the energy is quantized. There's only certain levels that it can go at. And this was a huge step forward also. It also kind of fits with the photoelectric effect stuff, because we could say, all right, if light has this particular, if a packet of light has a particular energy, well then maybe we can relate that energy to the energy that it that happens when the electrons move, and maybe that's why only these types of light have enough energy to liberate the electrons from these things, because they're causing the electrons to then be pushed out to these higher levels and eventually to be removed. So we'll do a little bit more calculations with those later. Oh, I want to talk about this too. I'm just worried about time here. All right, we'll talk about one more thing. And then we'll be done. I don't know what's going on with my screen there. Okay. All right, so here's another weird thing that happens. We're going to look at a few more pictures here. If you are shining some things at basically a wall, and there's a little hole in the wall, depending on whether something is a wave or whether it is a bunch of particles, it's going to act a little bit differently. If it's a wave, it gets diffracted, which means it kind of gets pushed off course and recombined. If it's a particle, you would expect the particles that are lined up with the hole to go through the hole, the particles not lined up with the hole to stop at the walls. Make sense so far? Okay. If you use multiple slits, you would expect the expected behavior with particles. So the ones that are lined up with the holes just go through the holes. The ones that aren't lined up with the holes just stop at the walls. But with waves, they're going to be a little bit different because they can combine in different ways. If you imagine like a bunch of water waves pushing up against a wall that had some holes in it, it wouldn't just all stop and the waves only go out through the holes. You'd get like a whole different wave pattern on the other side of the holes. And that different wave pattern that you get is called diffraction. And it would look something like this in this example. So you've got these waves that go up to this thing, and then they hit these slits, and some new waves form in some different ways. Sometimes they're constructively interfering, making bigger waves. Sometimes they're destructively interfering, kind of flattening themselves out. And then if you kind of add all that together, you end up with this thing called a diffraction pattern that's a regular repeating marker of all of this. And there's a video that I don't think we have time to do today, but maybe we'll look at it next week, that kind of shows an animation of how this happens. Okay, so that's just a difference between waves and particles. But what's happening now is in our discussion, or in what people are finding, is it's this difference is starting to break down. Light is being described as being these little particles, these packets of light. And some people are starting to say, well, wait, maybe matter, maybe what we think of as particles could actually be acting like waves sometimes too. And so they proposed some experiments to try this. So Yeah, okay. So if you shoot a beam of electrons at the similar type of slits, you would expect, and this is a little hard to see, let me see if I can make this a little bit bigger. There we go. So you're shooting electrons at some slits. Electrons are particles. So you would expect them to have particle behavior. The electrons that are not lined up with the slits should stop, and the ones that are lined up with the slits should go through the slits, and you should see two bright spots on your film behind the slits. Make sense? All right. So what actually happens when you shine a beam of electrons through some slits? You get a diffraction pattern, as though you were shining waves through the slits, as though you were shining light. So even though it's electrons, individual electrons, that you're shining through there, you get the diffraction pattern. And so people said, that's weird. That's not what we would expect at all. What if we can shoot electrons through one at a time? If we shoot them at one at a time, then we know that it's only going one at a time. Either it's going through the slit or it's not. We're not going to get an interference pattern. So you shoot a single electron, you actually still get the same interference pattern, as though the electron splits up into multiple things, goes through, recombines with itself, and forms a diffraction pattern, or is essentially acting like a wave. To get even weirder, if you use a laser behind that electron source, behind those slits, to sort of like track where the electron went, all of a sudden, the electron goes back to doing what you expected. And it's acting like a particle again. If you try to track its position. So that's super weird. So a lot of people were really upset by this. Einstein was one of them. Kind of didn't exactly refuse to believe it, but basically said, like, that, I don't know, I can't really handle that. But then a bunch of younger people kind of said, you know what, this is what we see, and this is what's happening, so we're just going to go with it. And we're going to describe it, we're going to see how it works. And it ended up being kind of the foundation to what we call quantum mechanics today. This idea that, in fact, waves, what we think of as waves, as light, can be both a wave and a particle. And what we think of as particles, whether it's electrons or balls or whatever, we can actually also describe as waves. And there's only certain conditions where that becomes really important, but they do, in fact, exist. So we will get into more of the calculations and the consequences from that. Yeah.
Is there going to be a quiz before the exam on Thursday?
Yes. So let's do. No, I think the. Is there any quiz on the? There's no quiz on the schedule for next week, I think.
Monday, isn't it?
I don't think it. Is there?
I thought
Take
I
a look
saw
at
the
it.
syllabus.
So I have the syllabus up.
Yep. What does it say?
Week. It says Monday, June 17th.
There is a quiz on Monday. So let's move that to Wednesday, so that it's closer to the exam, because we'll still be doing more new stuff on Monday, and then we'll have a chance to test that before the exam on Thursday. And 7, and maybe a little bit of 8 if we get there. We'll see. Any other questions about that stuff before we talk about lab? Okay, let's take a look at tomorrow's lab.
Wait, so have we finished all of chapter 7?
Not quite.
So what about the homework that's due Sunday night that's involving chapter 7?
Yeah, that'll have to be. We'll have to move that back.
To Wednesday? Or to Thursday?
Yeah.
Maybe we'll have all the information or to do the homework.
Right.
correct?
Yeah. And honestly, I think you should be able to do it if you look. So the applications of what we're doing, of what we've just talked about, is the last bit of chapter 7, and I think you can probably figure it out. But we'll talk about it on Monday for sure. All right. So tomorrow is the acid-base titration lab. As we said, there's no formal pre-lab assignment for tomorrow. How many people have done titrations before? So most, maybe a little over half, something like that. All right, how many people have done really good titrations before?
Done what?
Really good titrations before? Like you really nailed it? Maybe? We'll find out. So we want to get ready for this, for the lab tomorrow. Prepare your notebook as you usually do. So make sure you have title, date, purpose. This should be a pretty straightforward lab. So if you want to set it up nicely with like places for your data, you should be able to expect what you need. One of the chemical suppliers, Flynn Scientific. Tomorrow, as you're preparing your notebook, I think well, but also doing them quickly and efficiently. So whereas in the past you may have taken like a whole lab period to do a couple titrations, we want to really be able to knock them out and still have them be really good. So doing many titrations in a relatively short period of time. And then the reason for doing the lab now, this lab, it really isn't that interesting. It's just some titrations. But our lab next Tuesday, I think, is a really good one, and you need to have good titration technique to be able to get good results for that one. So that's why we're going to do this and focus on technique on Thursday, and then we can really have a great lab on next Tuesday. All right, questions? Okay, if stuff comes up homework-wise, let me know. And yeah, practice up for the exam on Thursday. Yes, Chris.
So since, well, actually, the first one is here tomorrow. Can I will I have before or after a lab since
Can I just send it in?
No. You gotta do the lab. But this is one that is possible that you can potentially make up.
Well, I'm making some food and I'll
If
send
you
this
want, yeah,
What about, oh, right, so Tuesday, that's the day to do Thursday classes, I have to PA for work in my garage, and I have to wait, my dad said it's at 12.
Do an internship.
What can I do?
So, probably the same thing that I was telling you originally, that if you want to make up that lab, you can find when the other class is doing it, the class that's doing it behind us, and ask one of those classes, one of the other ones throughout the day, if you can come in and do it in that class. Or you can wait and see, and because we dropped one lab, so you can just take that your drop lab, as long as you don't have to miss it.
Rather not.
Yeah.
I don't know, I don't wanna like take any chances, because like, what if I'm like sick from it, you know?
Right. But like, you're not gonna be able to make that one up for 2 weeks anyway. So like, by the time you would make that up, I think we'd be pretty much done with our labs anyway. So you know by then, like, you know by then anyway.
So you recommend taking it as a drop lab?
No, I think we'll just find out. Like, so I don't know. Let's look at the schedule
You'll
instead of just
know-
guessing
so
about
by
it.
the time you can make it up, it'll be the end of the thing, and it'll know if you have to make it up.
Let's see if that's true. Hold on.
Okay, so you might not miss any labs other than that one, and if that's the case, then that can be your drop one, but if you end up missing another one, then you still have time to make it up.
Yeah,
Yeah. So the acid base. Yeah. So the acid base titration lab on Tuesday is on Tuesday. Or no. Oh no. The acid lab is on Tuesday. Okay. So then 2 weeks after that, when the other classes would be doing theirs, would be the week of July 4th, which we're essentially done with labs by now, by then.
Okay.
Because this last lab is one that you can do that you don't actually have to be there if you have to miss it. You can make that one up. So if you had to, like if you, for instance, if you got sick and then you missed the flame test lab, well then you'd want to make one of those up.
Okay,
You know what I'm saying?
okay.
It's still a good lab, and calculations-wise, I think it's worth like going through just on your own so that you know what's going on. But if you don't have a chance to actually do it, because I don't think that's one that we can just like do real quick before class sometime, or because it's a kind of a setup.
If I have to leave at 12, should I still come to class? Is there something that I can do while I'm there?
I mean, you can get started with it if you want, or not.
Okay.
Yeah.
I mean, I would rather get started with it so I have some kind of background, right?
It's up to you.
Okay.
It's a pretty. I mean, I would expect that lab to take the whole period, so you'll get something started.
Okay.
But yeah, it's up to you.
Okay.
So when you
Oh, I forgot to stop my recording.